Welcome to WikiPodcast. Imagine a world where particles don't just exist in one place, but many at once. Or they can literally tunnel through solid barriers without, expending any energy.
Yeah, sounds impossible.
Exactly. A world where just looking at something changes its very nature. If that sounds like pure science fiction, well, welcome to the strange, beautiful, and frankly mind-bending realm of modern physics.
It really is.
Today, we're taking a deep dive into some of its most compelling mysteries: quantum tunneling, superposition, and the profound implications they have for the very fabric of our universe.
These concepts, they truly challenge our everyday intuition, don't they? They show us just how fluid and probabilistic reality can be at the fundamental atomic and subatomic scales.
Right.
We're going to try and unravel how matter and light behave in ways that, well, classical physics just cannot explain.
And why these seemingly impossible ideas are not only real.
Oh, they're very real, and they form the foundation of so much modern tech. Think about the sun shining or even the phone in your pocket.
So let's unpack this. Our mission today is to help you grasp these counterintuitive ideas, understand why they matter, and maybe discover the surprising ways they reveal a universe far more imaginative than we typically perceive.
How can our seemingly solid reality be built on such elusive probabilistic foundations? That's the big question.
Yeah, that's what we're here to explore. So at its core, quantum mechanics is the fundamental physical theory, right? It describes how matter and light behave at their smallest scales.
That's it.
And it's down there, below the scale of atoms, that things diverge wildly from our common sense.
Precisely. I think one of the most fundamental shifts from classical physics is the idea that particles aren't just tiny, distinct balls. They also behave like waves.
Wave-particle duality.
Exactly. So unlike the predictable billiard balls we imagine in our macroscopic world, at the quantum level, certainty is replaced by probability. The future isn't entirely set in stone. It's more like a landscape of possibilities.
And this isn't just about us not being able to measure things perfectly, is it? It's deeper than that.
Oh, much deeper. It's about the inherent nature of reality itself being kind of fuzzy.
Fuzzy. Yeah.
Exactly. In quantum systems, properties like energy, momentum, angular momentum, they aren't continuous, like a smooth ramp you can stop anywhere on.
Cool.
Instead, they are quantized. They come in discrete, specific values. Think of it like steps on a staircase. A particle can only be on a step, not hovering in between.
Right. Specific allowed values only.
Yeah.
So if particles are also waves, what's the most striking demonstration of this? The double slit experiment always comes up.
Ah, the double slit experiment. It's
Yeah.
truly iconic because it perfectly illustrates this paradox.
How does it work?
Okay, imagine shining a beam of light, or even firing individual electrons or atoms one by one at a barrier with two tiny parallel slits in it.
Okay.
On a screen behind the barrier, you'd classically expect to see two bright lines, sort of shadows of the slits.
Makes sense.
But what you actually see is an interference pattern, a whole series of alternating bright and dark bands, just as if waves were passing through both slits and interfering with each other.
So the particles are acting like waves, spreading out.
Precisely. But then, and here's the really perplexing part, if you try to figure out which slit a single photon or electron goes through,
You put a detector there.
yeah, put a detector at the slits to determine which path each individual particle takes. And guess what? The interference pattern just vanishes. Gone. The particles then behave like classical particles should, each passing through only one slit or the other. You get just the two lines you'd initially expect.
Wow. So the act of observing, it changes everything.
It seems to. It's as if the very act of measuring forces the particle to choose a definite path, collapsing its wave-like possibilities into a single particle-like reality.
Yeah.
It's a profound revelation about observer and observed.
Okay, that wave-like behavior, where particles seem to explore multiple paths, that leads us to another truly astonishing quantum phenomenon: quantum tunneling. Our everyday experience tells us, if a ball doesn't have enough energy to roll over a hill, it just won't. It stops.
Right. It gets stuck.
But in the quantum world, that ball might just spontaneously appear on the other side.
It's a purely non-classical effect. A particle can cross a potential energy barrier. Think of it like that hill, even if its kinetic energy is technically smaller than the barrier's height.
Classically impossible.
Utterly impossible. Classically, that particle would be trapped forever, but quantum mechanically, there's always a non-zero probability, however small sometimes, for the particle to simply tunnel through that otherwise impenetrable wall.
And this isn't just theory, it has real consequences.
Oh, absolutely. Profound implications, not just for the universe, but for our technology, too.
Okay, tell me about the universe part first. How does this shape things?
Well, for one, quantum tunneling is absolutely essential for radioactive decay, where unstable atomic nuclei spontaneously transform into more stable ones.
Yeah.
Without tunneling, many elements just wouldn't decay the way they do. And maybe more dramatically, it's a key process enabling nuclear fusion in stars, including our own sun. The nuclei in the sun's core, mostly hydrogen, they repel each other strongly because they're positively charged. Classically, they don't have enough kinetic energy from the heat to overcome that repulsion and fuse together.
How do you fuse?
They do, because they can quantum tunnel through that energy barrier. They don't need to go over it. They can sneak through it, probabilistically. Without that tunneling, stars wouldn't ignite. They wouldn't burn the way they do.
So no heavy elements, no planets.
Probably no life. The very matter we're made of owes its existence in part to this quantum weirdness.
That's incredible. Okay, and you mentioned technology. Where does tunneling show up there?
It underpins several crucial technologies. For instance, the Scanning Tunneling Microscope, or STM.
Right, the one that images atoms.
Exactly. It works by measuring the tiny electrical current that tunnels between a very sharp conductive tip and the surface you're scanning, just nanometers away. The current is extremely sensitive to the distance, so you can map out surfaces atom by atom.
Amazing precision.
And it's also vital in certain electronic components, like tunnel diodes and tunnel field effect transistors. These devices use tunneling for faster switching speeds and lower power consumption. They're really important for cutting-edge electronics.
So tunneling lets particles pass through barriers. What about superposition? That's the idea of being in multiple states at once.
Yes, superposition. It builds on that idea of possibilities. It suggests that until we measure it, a quantum system isn't just one thing. It's a blend, a combination of all its potential outcomes simultaneously.
A blend. How does that work?
Mathematically, a quantum state can literally be a linear combination. Think of it as a weighted mix of its possible basic states, its eigenstates. So a particle isn't just here or there. It could be in a state that is partly here and partly there at the same time.
Or spinning both clockwise and counterclockwise.
Exactly. Until you make a measurement that forces it to choose one or the other. It's not just that we don't know the state. The state itself is this combination of possibilities. All possibilities genuinely coexist.
Okay. How do we actually see this in action? Is there an experiment like the double slit?
There is. The Mach-Zehnder interferometer is a good example. Imagine you send a single photon into this device.
Oh, wait.
It hits a beam splitter, which is like a half-silvered mirror. Classically, the photon will either reflect or pass through, but quantum mechanically, it enters a superposition of both paths. It effectively travels along a lower path and an upper path simultaneously.
Both at once.
Both at once. Now, if you put detectors on those paths to see which way it went, the superposition collapses, and you'll only ever detect it on one path or the other.
The measurement problem again.
Exactly. But if you don't put detectors there and instead recombine the paths with a second beam splitter, the photon interferes with itself.
Interferes with itself?
Yes, because its wave function traveled both paths. The pattern of detection after the second beam splitter proves it must have been in a superposition of taking both routes. It's a powerful demonstration that particles genuinely explore all available options until forced into a definite state.
This really highlights the crucial role of measurement. This whole measurement problem seems central. It challenges our fundamental idea of an objective reality just existing out there, doesn't it?
It absolutely does. The probabilistic nature of quantum mechanics seems intrinsically linked to the act of measurement. Before measurement, you have this superposition of possibilities described by the wave function. Upon measurement, it appears to instantaneously collapse into one definite state.
And this was the core of the Bohr-Einstein debates, right?
Precisely. Einstein found this probabilistic element deeply unsatisfying. He wanted a deterministic, objective reality underneath it all. Niels Bohr, on the other hand, argued that quantum mechanics is complete, and we have to accept this probabilistic nature and the role of the observer, or at least the measurement apparatus.
It leads to those weird thought experiments, too, like Wigner's friend.
Right, where you have an observer inside a sealed lab measuring a quantum system. To them, the wave function collapses. But to Wigner, outside the lab, maybe the friend and the system are still in one big superposition until he opens the lab and looks. It asks profound questions. What counts as a measurement? What counts as an observer? When does reality actually become definite?
And this idea of interconnectedness, where quantum systems can be linked, That brings us to entanglement. Schrödinger called it the characteristic trait of quantum mechanics.
He did. Entanglement happens when two or more quantum systems interact in such a way that they become, well, linked. Their fates are intertwined.
How so?
Their properties become so deeply correlated that you can no longer describe the state of one without considering the state of the other, no matter how far apart they get. They share a single unified quantum state.
So if you measure one...
If you measure a property of one entangled particle, say, its spin, you instantly know the corresponding property of the other particle, even if it's light years away across the galaxy.
Instantly. That sounds faster than light. Einstein's spooky action at a distance.
He called it that because it seemed to violate locality. But it doesn't transmit information faster than light. Still, it shows this incredibly deep, non-local connection. They behave as one system, sharing a single quantum superposition until measured.
And entanglement isn't just a theoretical curiosity either.
Not at all.
Yeah.
It's absolutely fundamental to the development of quantum computing, where entangled qubits can perform calculations impossible for classical computers, and quantum communication, like quantum key distribution for potentially unhackable encryption.
Wow.
Plus, entanglement has been used in experiments testing Bell's theorem. These tests have consistently shown results that violate inequalities based on local realism, the idea Einstein favored, combining locality with the assumption that particles have definite properties even before measurement, hidden variables.
So the experiments support the non-local weird nature of quantum mechanics.
Overwhelmingly. It seems entanglement is a fundamental feature of reality, defying our classical intuitions about space and separation.
Okay, my head is definitely spinning now. Particles tunneling through walls, being in multiple places, linked across space. Let's add one more. The uncertainty principle. This isn't just about our tools not being good enough, right?
No, absolutely not. It's not a limitation of our measurement devices or techniques. It's a fundamental consequence of the mathematics of quantum mechanics, stemming directly from that wave-particle duality.
Okay, what does it state?
It states that there are certain pairs of properties of a quantum particle called complementary variables that cannot both be known or predicted with arbitrary precision simultaneously. The classic example is position and momentum.
Position and momentum. So where it is and where it's going, essentially.
Kind of, yeah. Momentum is mass times velocity. The principle says if you measure the particle's position with very high accuracy, your knowledge of its momentum inherently becomes fuzzy, less precise.
And vice versa.
And vice versa. If you measure its momentum very accurately, its position becomes inherently uncertain. There's a fundamental trade-off baked into nature.
So you can know one really well, but only at the expense of knowing the other.
That's exactly it. Think about a wave again. A wave that's spread out over a large area, its position is very uncertain. But you can measure its wavelength and therefore its momentum quite precisely.
Okay.
Now try to pinpoint the wave's location. You have to squish it down, make it a short wave packet. Now its position is well defined, but it's made up of many different wavelengths superimposed, so its momentum becomes very uncertain.
So it's inherent in the wave nature.
It is, and this applies to other pairs too, like energy and time. It means, for example, that particles can briefly borrow energy, violating energy conservation, as long as they pay it back quickly enough, which is related to virtual particles in quantum field theory.
Wow. Okay, so these ideas, tunneling, superposition, entanglement, uncertainty, they sound incredibly abstract, almost philosophical.
They do.
But you're saying they have huge practical successes. They actually explain our world and drive technology.
Absolutely. Quantum mechanics isn't just speculation. It's arguably the most successful scientific theory ever developed in terms of predictive power. It's the foundation for almost all of modern physics and chemistry.
Like what specifically?
Well, solid-state physics, which gave us transistors, semiconductors, microprocessors, the heart of all our computers and electronics, is entirely based on quantum mechanics, understanding how electrons behave in material.
Okay, computers. What else?
Lasers, from barcode scanners to Blu-ray players to fiber optic communication carrying the internet, LEDs, the efficient lights in our homes and screens. Even medical imaging like MRI, magnetic resonance imaging, relies on manipulating the quantum spin of atomic nuclei in your body.
MRI, right. I hadn't connected that to quantum mechanics directly.
Yep. And beyond tech, it explains fundamental things. Why matter is stable, why atoms don't just collapse, why solids are rigid, the nature of chemical bonds, how atoms join to form molecules, including complex ones like DNA. Its predictions match experiments with stunning accuracy.
The magnetic properties of an electron, I read somewhere, match theory to, like, 1 part in a trillion.
Something like that, yes.
Yeah.
The agreement is extraordinary. It works incredibly well.
It's truly amazing how these bizarre rules at the micro level build up the seemingly stable, predictable world we experience macroscopically. But despite all that success, the philosophical side, the interpretation, that's still debated.
Oh, very much so. There's still no consensus among physicists about the correct interpretation of quantum mechanics. What does the math mean for reality?
Richard Feynman's famous quote.
I think I can safely say that nobody understands quantum mechanics. He meant understanding it intuitively, I think. The math works, the predictions are phenomenal, but grasping the underlying reality it describes, that's tough. The debates center on that probability, the wave function collapse, non-locality.
We touched on the Copenhagen interpretation, Bohr's view, sort of embrace the weirdness and the role of measurement.
Right. That's been historically dominant. It's pragmatic. It says quantum mechanics tells us what we can know from experiments, and maybe we shouldn't ask for more.
But Einstein wasn't happy with that. He felt it was incomplete. God does not play dice.
Exactly. He deeply disliked the randomness and the non-locality. He thought there must be some deeper, deterministic, hidden variables that quantum mechanics wasn't accounting for.
But those Bell tests you mentioned seem to rule out his preferred type of hidden variables, the local ones.
They do. The experimental results are inconsistent with local realism. So if there are hidden variables, they'd have to be non-local, which is arguably just as strange as standard quantum mechanics. It shows how deep the weirdness goes.
And then there are the more out there interpretations, like many worlds.
Right, the many worlds interpretation, or MWI, proposed by Hugh Everett III. It takes the mathematics of quantum mechanics, specifically the wave function, completely literally.
How does it avoid collapse?
It says the wave function never collapses. Instead, every time a quantum measurement could happen with different possible outcomes, the entire universe splits or branches into parallel universes, one for each outcome.
So in one universe, the particle went left, and another it went right.
Exactly. All possibilities are realized, just in different non-interacting branches of reality. It avoids the measurement problem and preserves determinism, but, well, the price is an unimaginable, perhaps infinite number of parallel universes.
That's quite a price.
It is, and it's just one of several interpretations out there. Others include Bohmian mechanics, consistent histories, relational quantum mechanics. There's no shortage of attempts to make sense of it all, and the search for a theory of everything uniting quantum mechanics with general relativity, gravity that's still the holy grail, driving work in things like string theory and loop quantum gravity.
So our deep dive into quantum tunneling, superposition, entanglement, uncertainty, it really hammers home that the universe at its most fundamental level is far more mysterious and frankly imaginative than we could ever have conceived.
Definitely.
It just completely challenges our classical intuitions, expands our idea of what's possible, and even shows us the inherent limits to what we can know.
It's a constant reminder, isn't it, that our everyday view of reality is just an approximation, a very good one for our scale. But underneath, there's this deeper, probabilistic, interconnected, and frankly, quite bizarre reality. The universe definitely likes to keep us on our toes.
It certainly does. Thanks for listening. Write us your opinion in the comments on what you find most mind-bending about quantum mechanics. Is it tunneling, superposition, entanglement, or something else? Subscribe to the channel to help more listeners reach our deep dives. Thank you, and have an amazing day.